have done so far. Okay. So correct me if I'm wrong. It's written for your assignments, rather small problems. You want to solve very small non-algorithmic problems, some problems that require some algorithm. Okay. And when I say small, okay. Now, even if you have written, I doubt how many of you have written, even though you have programmed, anything more than a few hundred lines. Okay. So correct me if I'm wrong. One or two people will always be there, maybe. Okay. But it's my experience that most of the students at your stage would have written like very small programs. Obviously, assignments even beyond. And a few hundred lines is very small. A 500, 600, 700 line program is considered to be very, very small. Your entire program usually resides in one file. Some of you know how to break things and so on. But most of you rewrite everything in one file, basically. Okay. You declare your prototypes in one file, any hash defines, you have to do, write all your functions, then the main function. So everything comes in one file, you compile that file and then you run it. Okay. Debugging, now this is one place where people who are more experienced, some of you who are more experienced in programming, may have done it by some other means, you know how to use development environments and so on. But what we have taught you so far is mostly you debug when something does not work by putting printfs. Your program is giving a segmentation fault access violation. Okay, you want to know which part of the code it's coming from. You put printfs in different parts and then you see which printf, or the first one is getting printed, the second is not getting printed. So my error must be somewhere within this. Your value is not coming correct. You want to print out intermediate values of a variable, you print them out. Now, every time you insert printfs, you have to recompile and then run the program again, so that the prints come up. Okay. This is always, almost always written only by you. Okay, hopefully, of course. Okay, but you write your own programs, your assignments, your problems, and so on. And the other thing, no one else uses your program. Again, for your assignments, hopefully. But again, jokes aside, you want to submit something for your assignment, you submit something for competitive coding, whatever it is. So you write programs that are meant to be used by you for some specific purpose, like getting marks for an assignment or something. And if you want to reuse some part of your program, okay, if you want to reuse some part of your program, so I give you an assignment and you say, oh, the sorting code I have there anyway. I've already written the sorting code. Typically, what do? You go to that part, you cut and paste the sorting code into your new program, and then maybe you change some variable names and formats a little bit, and you do that. Okay. So reusing your parts, some other part needs cut and paste your source code. So this is typically what you have done. Do we agree? Anybody wants to say anything at this point? Please be interactive. Feel free to ask questions, comment, and so on.
Sir, will you teach us how to use debuggers?
I'll come to that. Okay, that's what the introduction is about. Okay, please wait. But so far, what I have said, I think this is what programming meant to you. Okay, and that's fine to start with. The other thing is that your programs disappear when courses. This is a very, very critical point. Okay, so bear with me for 5 minutes. You do a program, you do for your algorithms class. You've written some programs. When the algorithms course is over, usually your programs you don't care about. You may save them, store them for your future references, something, but usually it doesn't matter. Okay, when you lose interest or whatever purpose that you have used it for, there's gone. So that's what the programming environment that you have so far. Now, the real world of software development is very, 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 very different. You will not be writing only by you. You will have large projects with groups of people working together. Now, what is large depends, okay? But there will almost always be some group of people. The software size nowadays is such that it's usually never written by one person. There will be exceptions, but you will never written by one person. You will write a part of it. And the overall software, just think about everything that you use. You think about your Facebook thing, you think about a Google search, everything will have many, many features, services, whatever you call it. And this will be complex software with hundreds of thousands to many millions of lines of code and spread over hundreds and thousands of files. This is not going to be one file with a few hundred lines of code. Okay. And you write only part of it. The other people will write other parts of it. Maybe you will reuse some parts that are already out there. Okay. There will be some common parts that are written by many people. So for example, in the old days, okay, when we used to work and so on, actually wrote a lot of code. So there was in Windows, there was this file called winerror.h. So you will write your part of the Windows and so on. But then if you want to introduce a new error code, everybody will have to go to that one file and introduce their error codes. There were specific places, groupings and so on. But that one file will be modified by almost the entire set of people. But then everybody will work on their respective parts of the project. Other people, so obviously, if the software has many features, many services, you write only part of it, but the software has to work as a whole. Other people, so these two things will go hand in hand. Other people will use what you write. So for example, you will write a bunch of functions that somebody else will call. Okay. And similarly, you will call some functions that other people use, other people write. All right. You think about an operating system. You have done, your C library, you have done malloc and everything. It's nothing but a piece of code that somebody else wrote. But it's there for you to use. So you use whatever is there. Similarly, in a large piece of software, you will also write some functions and something that the other people will use. That's what the real world will do. And some codes will be used out of this for a lot of people. So these three last bullets kind of go hand in hand. You will use something that the other people write, other people will use something that you write. And now within this usage also, some parts will be used by a lot of people. Classic example is when you write the code for an complete operating system malloc. Even inside the thing where you have, operating system will use malloc, the kernel version of it, but will do memory allocation and so on. Printing, okay, will be used by everybody almost. All right. And this is a big thing. Your code stays when you leave the project and company. You join a company, you get assigned your job. You wrote like 2,200,000 lines of code over 5 years, but then you leave the company. It's part of the software. The code does not go. Okay. So the code stays there. We'll see. We'll look at each of these points and we'll see what issues they give. But this is what, if you look at by like what your the way your program looks like so far and what happens in the real world, they are very different. And one basic goal of this course, I will elaborate that on the later slide again, is to kind of get you tuned to this. It's not that we will be able to write very large programs because that takes a lot of time and so on. But we want you to start thinking about doing certain things the right way when you write code. So you can carry forward those habits when you actually get into these large programs. Obviously, in your projects and all, as you go on, you will write much larger programs. Students have written code programs that are a few thousand lines or so and so on. But you will probably not encounter hundreds of thousands of lines of code or something in BTech. But you still want to be tuned to that thing, so you're already ready for it. So, given that this is what the real world looks like, what issues, problems that arise? Take each of them. You have large number of, how do you organize them? First of all, you want to write this huge piece. What are the rules and guidelines for breaking up your program? Is it that you break it up arbitrarily? Okay. So right now I'm just trying to talk you about the kind of problems that you have to solve. And in the next slide, for each of them, we'll see which are the ones we'll address in this course and a little bit about the other ones, basically. So let's not think about solutions right now. So what are the rules for breaking up your program? How do you organize the files? Because when you have 10,000 files, how do you know what is where and so on? You want to change something, which part of the code contains what and so on. Basically. How do you compile the files? Would you do like CC that you have done, GCC or whatever your simple compilation in code block and all you have done? And you but then you have like specify all the .c files. That sounds too bad, right? How do you even keep track of all the files in a project? Like different people will be, kind of adding files intermittently. Some files will get merged and will get deleted. So that will give you an error if you try to compile. Okay. So how do you do this? Then comes the question. Suppose you have 100 files. What if you changed only a few files in one line? Now you compile only one file, two file, and so on. So compilation hardly takes any time. But in the real world, building something, we call the process building, the software, can take a lot of time. And building everything from scratch, which is usually referred to as a clean build. Okay. So you build everything from scratch. You assume that all files have to be compiled and from afresh and so on. Okay. Sometimes can take hours. Literally. But then if you have just changed like a few lines in 3 files and you have 1000 files, you don't want to compile all of them. And but then how do you handle dependencies? You may have changed only a few files. Say you changed something in one function. Stop me if you don't understand anything, okay? So suppose you change this one line in one function, in one .c file. Okay. What all needs to, so there may be other files which call that function. The question is, do they have to be compiled again? But then is compile a monolithic process? That so far that's what you have seen. Everything is done for you. You compile and then you get the executable to run. But we'll see there is a process of compiling, linking, and so on. So in this particular case, for example, you should compile only that one file, but the linking has to be done afresh. But then, there may be other dependencies like you change one prototype, you change the hash define. Now other people may be including your file somewhere else. So how do you keep track of this when you have like thousands of files? And then what somebody was asking, how do you debug when your program does not run correctly? Debugging with printfs is very inefficient. It requires you to recompile your program every time. So how do you debug? And the related question is, what information can be helpful in debugging? So we'll come to all of this. How can codes be reused? It's a common requirement. Everyone should not have to write them. But cutting and pasting is not a good option. Because then think about that I have a sorting algorithm. Okay. And then these 100 other people wanted to use it. And they cut and pasted the thing. Fine. But then if I come out with a better implementation, faster implementation of that sorting algorithm, there are now 101 versions of it. I just update only one of them. How do I convey to the others? How do I even know who all has cut and pasted my code? So there has to be some automated way of doing this. So that if I make a faster implementation of sorting, all those who wanted to use my sorting function should automatically get that faster implementation. So cutting and pasting source code does not work when the program becomes large and there's a lot of views and so on. And how can we make it easy for others to use your code and you to use theirs? Okay. So this kind of related question. Then coming to that, some parts are, some files are used by a lot of people or written by a lot of people. You and I write to a common file. That Windows example that I gave. How do I ensure you will not overwrite something I wrote and vice versa? Is it that I need to know everybody who is going to modify the file? Send a mail to all of them, hey, I'm changing, nobody should change. That doesn't sound right. Okay? And remember, this is a very critical thing. I have been called in the middle of the night because the clean build of Windows has stopped because somebody overwrote my error code because they did not follow process. Now that does not, should not happen. Fine, it was easy to fix, but then You understand, without coordination, if everybody goes and modifies a file, there's always a chance that something will be overwritten by somebody else. Everybody cannot write together in the 10th line. There will be garbage in the file. Similarly, your code was working 10 days back. This is again a very common occurrence. You added some more code, but it's not working now. So you want to go back to the 10 days back version and see what all you changed. See which one is causing the error. But then how do you know exactly what change you did in those 10 days? So that will help you isolate the problem faster. So you don't want to debug your entire code. You just knew that up to this point, the code worked perfectly fine. But then I added these couple of features and something is wrong. But then what features did I add? Which part of the code did I change? Because I know the error is coming from those parts. So does it mean that you as the developer need to keep a version with you every time you send? Can do that. I can keep backup copies and so on, but it becomes over a period of time. You understand, when you deal with one file, it's easy. When you have to modify hundreds of files yourself, okay, it becomes very, very tedious to keep the versions and so on. Okay. So these are kind of the problems that occur when you go into the real world writing real software. And competitive coding is not real world software. So let me digress and say one thing. It's important, it's fun, it's interesting, it helps you learn a lot. Okay. But the goals of competitive coding is to write programs very fast. Device, of course, there's a problem solving part of it. But once you know the algorithm, everything, okay, you want to write the program very fast. You don't want to again have anybody reuse your program or anything like that. Basically. Okay. So when I talk about the real world, I talk about the real industry code that you go and write. And this is the last one, that someone else may look at your code and will need to change, maintain it. You may be gone, the code stays. Somebody gets hired in your place. Okay. Features get added later on. Somebody will have to do that, and they're building on your code. So they have to understand your code and maintain it. So how can I make my code more understandable? And trust me, this is how important it is. So studies show, okay, I don't remember the exact figure right now, but it is not going to be anything less than that around 60% of the cost of a software over a certain period of years is in maintaining the software, not in developing it. So I don't know what the 60% figure is now, but maintaining the software, the cost of maintaining includes basically how much man hours you spend in adding new features, debugging things, because once you roll out the software, there will be problems. People will report bugs to you. You'll have to fix them and give a newer version. You give patches and updates that people can add. Your Windows machine does Windows update all the time. Okay. So when you write the code, you have to remember, and this is critical that I want to instill in you now, that you are writing the code so that others can understand it. Of course, you have to understand it, but write the code such that others can understand it. That is very, very important. Any questions so far? Okay. If not, so these are all problems. Okay. So what are we going to do about it? So we're going to look at each of these issues, and we are going to say what we are going to do about it in this course. Some of them we will not do in this course because they don't fall under the purview of tools and so on. But we'll still discuss each of these issues. Oh, okay. There is one more thing. I think this is the last one. Yeah. So your code runs correctly. So now you have written correct code. You have managed all these other issues and so on, but it's too slow compared to what you need. How do you know what's slowing it down? It's a huge piece of software. So where do you start? Wouldn't it be nice to know which part of the code is taking how much time? So you can give some inputs and say, this function is taking a lot of time. So let me see whether we can optimize that function. But how do you know? Because you run the program, it takes a total time. That's it. It doesn't tell you the breakups and so on. So what we aim to do? We aim to introduce you to some tools that help you with some of these issues. Okay. And this is what I've been stressing. Important to remember what issue you're addressing and why you need to address it, rather than just mechanically learning the tools. So it's very easy to get engrossed in learning the tools. Look at all the features, 30 different features, and you feel great. I know all these things, I'm the God. But if you do not understand why you are learning it, what is this business of large software development, what problems you're solving, okay, when the time comes, you probably will not be able to do it. So you want to instill the habit, okay. So we'll only do some features. The full feature set for some of them are quite extensive. And then you will encounter other tools in future that will be better and easier to use. Your software engineering course will kind of talk about some of these same tools and some other things. So what we are going to do is mostly command line tools because they are kind of the base. But you have GUI based wrappers around these tools because so we do these tools because they're kind of universally accepted. But then GUI based tools, sometimes they're commercial, sometimes open source. Some people like this graphical interface, some people like that other. Somebody like code block, somebody like something else. Okay. But your code block will use these compilers, these debuggers, and all also, whatever code block is doing. Okay. So these are kind of the base tools for many of them. There are other tools also. So when you get those tools, we use them. You want to do things faster and better. But as I said, important to instill some good habits early on and practice it for every piece of code that you write. Even though you're writing small piece of code, it may not always be necessary. And some of these issues will become more clear as you take other courses. Some of these things are very OS dependent. So, some of the terms, kind of things will be kind of little bit alien to you right now. But when you read those OS course, it will become very simple. Okay. So I'll use the term attached to a process. Okay. You don't know what it means to attach to a process. You don't even know what a process is here. Okay. We just want to start you up. There will still be enough tools, enough features will teach you, enough things. Okay. But you want to instill these habits also. So we'll take each of those issues and we'll see what we do. How do you organize the large number of files? We'll take C programming only. We'll discuss how to organize into .h and .c. First of all, which one should go to .h, which one should go to .c. These are the two things that you have in C program. But there are some clear guidelines for that. And breaking up into multiple files, that we will not really teach you. They follow kind of intuitive guidelines. There is no hard and fast rule. Basically, you want to put relevant things into a single file. Okay. So you are developing a complex data structure, priority queue. You want to create one .c file, all the functions regarding that in one file. So you look at that file name, I know basically that this is something to do with priority queue. Okay. So now how much to put, whether you will put all data structures in one file and call it data structures or C, or priority queue in one thing, stack in one thing, queue in one thing. That is kind of subjective, depends on how much large size the piece of code. There is no hard and fast rule. But intuitively, you try to put relevant things into a single file. Name them meaningfully. Never name files A.c, B.c, 1.c, 2.c, myfile.c. Always name the file mnemonically, meaning something regarding the content that the file carries. Okay. And then you hierarchically organize files. These are very standard things, folders, subfolders, and so on. Again, name the folders, subfolders very mnemonically. So no tools involved. This is not something that will go in. I think it's understandable. We can talk about it more later, but you should practice this. How do you compile the files? We'll discuss the issue. All those things that you say, how do you compile this large number of files and so on and so forth. How do you keep track of this thing? How do you keep track of the dependencies? How do you make sure that if you change a few lines, everything does not change, doesn't need to get compiled? So we'll introduce two very, very important things, GCC and Mink. We'll see what they are. This is the compiler. The CC compiler is actually, when you, okay, so, well, CC is Linux, so you may not have seen it always. Anyway, we'll come to that. But basically, C compiler, the different features that you have to do, different things beyond just generating the executable file, and make files to keep track of all the files, dependencies, and so on. How do you debug when your program does not run correctly? We'll discuss, and we'll introduce two debuggers, GDB So many of the GUI-based debuggers, the underlying thing in Linux-based systems is GDB. And we'll discuss another very interesting tool called Valgrind, very famous, very popular tool called Valgrind. Valgrind has many different components. Most of them you will not understand now. As I said that you have not done architecture, not done OS, but we'll do memory check on the kind of things that you have encountered even in your first year programming. You have declared a 100-sized array, but somehow in your for loop, you went to the 101th location. So you get an error. If, as I said in my lab, at least, if you are lucky if you get an error, because then you know something is wrong. Many of the times you silently pick up a garbage from that place and you will get it wrong. But can you do something so that when you run, things will get pointed out that that for loop is actually accessing an array out of bounds. Okay. Then we know that every malloc you should do a free. We have not followed that rigorously because you write very small programs. But in servers that run throughout the year, basically. This is the other thing. Your programs come and go. A server runs continuously. So every time you make a Google search, for example, it's actually a huge set of servers. But think of it as one server, just as a layman's view. Okay. So one thread will get created, service your request, you go on. But the basic server will keep on running. You will get your request. Somebody will be waiting to get your request. Get your request. Create a thread. Thread will do its work. Terminate the thread. Give the result back to you. Now that's not how Google search works again. It's a whole bunch of servers behind it doing very complex thing, but that's the broad idea. But then the server runs throughout the year. Your telecommunication servers. And these servers are so critical that a downtime of like 1 hour in 1 year is sometimes considered to be too much. So there are other ways, okay, that I'm not going into, so that if it does fail 1 hour, it is that critical, something else will take over and so on. But you don't really want the server to, fail all the time. A server that fails every 1 hour every month is just completely unacceptable for this kind of works. Okay. But then, if you keep on mallocing without frame, ultimately you will run out of memory and your server will crash. Maybe each of those requests are only mallocing 5 bytes. But then if you don't free it, it's an additional 5 bytes. And when you get like over a period of time, over 6 months or something, 30 million requests or whatever it is, okay, Google is much more, of course. Then each of those 5 bytes add up and then you run out of memory and your server crashes. But then you have a huge program doing mallocing all over the place. You malloc somewhere, you remember your strcpy function. Okay, when you call strcpy, it actually mallocs inside the strcpy function. So you are supposed to free it if you don't need that thing. So it mallocs somewhere, frees somewhere. How do you keep track of that? So Valgrind has some very interesting tool, sub-tool basically. We'll teach you those very simply to show you that these are the things that you have not freed. Okay. How can codes be reused? The standard thing will teach you how to build static and dynamic libraries. What's the difference between them? So whenever, for example, you did -ln, you don't have to write the square root code. You just call the square root function. Okay? You don't have to write the printf code. That's in the stdlib, the standard library of C. Somebody has written the code. So you build libraries so that people can call your function. So if you change something, you just rebuild the library. People just need to link with it. Everybody's not like that cut and paste that everybody's code you have to go and change, add that line of new implementation and everything will have to be recompiled or anything. How can we make it easy for others to use your code? How can I call your functions clearly? You can call my functions clearly. Okay. Again, there is no tools involved. It's more coding practice. So all these things like, putting your files, mnemonic names and so on, define the interfaces, the prototypes very clearly, never change the prototypes. Okay, because you do not know who all have called it. Just think of the chaos that will happen if C suddenly comes back and says, no, this is not the prototype of printf. Printf will first take the variables and then take the format string. Yes, a toy example, but suppose somebody comes back. Now you have so many, millions and millions and billions of lines of code of C code already sitting there. They will all need to change. You have to go and change your printf calls everywhere, or they will not work because the order of the arguments will not. So you define interfaces, which is in this case prototypes, very, very carefully, and you don't change them. Okay, or changing will require you an internals of the organization, you change them, but that needs to go through. You cannot just suddenly one morning say, no, I think I'll add one more parameter. No, I think I found the first time I don't need that parameter. You just cannot do that. But that is coding practice. There's no tools involved out there. Same thing for the next two bullets, kind of common thing. How do I ensure I don't overwrite your things? How do I ensure that I go back and get any version, compare with the version? Any software development process in the real world will use a version control system. There are several of them. Your Git is one of them. You have heard about it. So Git, CVS, SVN, the very famous version control system. Will teach you one. Okay, somewhat. But again, the idea of the version control system, you should see like why you need, what can you do. You go to something else, the syntax will be a little bit different and so on. But the kind of things that you will be able to do with a version control system will still be similar. Okay. What about this other thing that I said that somebody will need to maintain your code, change your code? How can I make my code more understandable? This is again coding practice. You need to put in comments. Now, how much comment is good and bad? That's subjective. You put too much comments basically, then I'm only reading your comment. I'm trying to find where is the code in there. Okay. There are coding standards to be followed. Okay. There are variable naming standards. The different organizations have different kind of internal standards and so on. But some things are generic that you can practice anyway. As I said, comment anyway, even if you don't know how much to comment. For example, every function that you have, you always start a function saying, one comment saying which parameter, one line for every parameter describing what the parameter is doing. One line saying what will it return. And one line saying overall the description of the thing. You add a for loop, you kind of add a comment before that saying what is the loop? If it is anything complex. It's a little bit subjective. You don't want to do it for every for loop. There's no rule like that. If you're just initializing an array every element to 0, you don't want to write a comment before that. Somebody looks at it, it's obvious. But you have a thing and you're doing some computation over arrays inside a for loop, you might want to add a thing that this loop, this part of the code does this. Okay. Then using variable names, you never use variable names like int x, int y, and so on, even though you will see sometimes us doing the same thing. Okay. But I think you should get it in the habit. Okay, because when we teach you something simple. We should be careful also. But you make a practice that never name a variable ij for temporary variables are fine. But if you have a variable that whose purpose is to sum, never say x or s. You start sum. Okay. You have seen some of this. Count should be like cnt count something from which the name you can kind of little bit understand at least the purpose of the variable. And then finally, the last part, your code runs correctly, but it's too slow. How do you know what is slowing it down? So again, we'll discuss issues and we'll introduce to another very famous tool called gprof, okay, which you can run from the command line, and you can do that. So some of those tools, gprof version of the things in the red, will teach you. And then the part 2 will be the Linux part. So all these tools you will find in the real world, either with a wrapper around them or directly used. Okay. And you should practice using them. We'll teach you some features of them, but you should practice using them when you write code, basically. And part 2 is kind of simple. Okay. We want you to start using Linux as soon as possible. It's a widely used OS in practice, especially in servers. While Linux and other flavors of Unix, Linux came from Unix. And then different companies there are different flavors of Linux also and so on. So it has like 40–50% of the world's server market share. It's open source, easy to get. So many people use it not just for servers, normal things or desktop, you'll see a lot. And as a CS student, you will have to navigate through Linux sometime or the other. So we better know it. Your courses like Networks OS, everything will require it also. Again, we don't intend to teach you the internal how Linux is designed and all those things. Okay, that's not our goal. And some of the issues will have to, some OS network terms will come that you do not know yet, maybe hard to understand, but in ask us, we'll see how to make it easier. Not much, not much. So we want to start you off with basic commands to navigate the system. Some of them you may already know if you work with Linux. But basic things to work with the file system, directory, write and run program, check different system status and so on. And we want to teach you shell programming, which is more like learning a programming language. But it helps you to create new commands, automate many repetitive tasks. And if you want to manage, as a system administrator, manage Linux system, shell scripting is a must. Yes. So that's what we will cover. That's all I have to say at the introduction. It's a long introduction. So as part of this, you understand all those tools that we talked about. Okay. You will need to work on Linux. So normally that happens from the first year itself when you have offline classes, because your labs, your C programming, the first year PDS programming happens in Linux. We do not do that in online mode because some of you at the very beginning learning computers for the first time may have trouble installing Linux and so on. So somehow you have to get Linux on your laptops locally. You can get a dual boot thing. It's an easy thing to do. So because you will need that. So I'll stop here. Do you have any questions now, or should I hand over to Eddie?
Sir, do we need to install Linux operating system?
Yes. You can install dual boot. That is what I suggest. Okay, if you can get local help and so on, because you will need that anyway. Okay, next semester onward, even there you will need that anyway. Okay. And there are, just if you are here offline, you can take help from your friends and so on, your seniors and so on. Third years are here already mostly. So find out people in your hostels and just ask for help. Otherwise, there are other ways. You can search in Google. On your Windows, you can install something called a virtual box and then install Linux. So you can run virtual machine, something called a virtual machine. Okay. Mac also has similar things. So you can start off that. Today, this week there is no assignment or anything to start off, but yeah, eventually you will need Linux. Basically. Not eventually, very soon. Yeah.
Sir, like, why do Mac you just need to install Linux? Because it's a Unix operating system anyway.
Which one?
Mac OS. It's also
Mac
Unix
OS.
based, right?
So Mac OS, you are saying. Mac
Yeah.
OS, this gprofs and all these things will not work directly. But there are simple ways. Just do a Google search. If any problem, contact us. There are simple ways to install all these. Valgrind, for example, you have to install all this. Now, some of them may have gprofs and all come bundled with Linux as something called GNU utilities. Okay, GNU utilities. So fine, check your macOS. If it's already there, you have done something with it already. But to the best of my knowledge, vanilla macOS, you cannot directly run it. But as we teach you, if you run these things, for example, I don't think GCC is there vanilla in macOS unless you do something. If it's there, then fine. As long as you can run the tools, we're happy. Start off, then you have any problems, it's fine. You can ask us. Anything else?
So about
Yeah, come again.
WSA, like Windows subsystem of Linux. Like
Yes, WSA is also there.
Yeah, so can we use that? Or
You
like
can see, let me put it this way. Let the class start. First tool, the GCC will start today itself. You can use whatever, okay, that gives you a Linux command window and you can run the tools. Because see, for GCC, make, gprof, okay, Valgrind, all those things basically will write C programs. and you will run them, but these tools run on Linux. Yes, you can use Windows Subsystem, WSA, and so on. Anything that you can open a Linux window. You can use VirtualBox and install Linux there. It comes equipped with Linux already. You can just choose it. Okay, so whichever way you do it is fine with us. Just find out the options. All you need to do is to basically those red things that I pointed out, GCC, make, all those things should run on a Linux command window, basically. Any other questions? Start off, then if you have problems, we'll see. Specific problems, we'll see. But we have to get this to work. Without a Linux window and these Linux commands running, the course will not run. Anything else? Okay.
Sir, do we need to be ready with Linux until the next class?
See, we'll start teaching you GCC this week itself. This week there is no assignment, so we'll complete GCC. The first assignments are anyways going to be very simple assignments and so on. So it is not that you must get ready with Linux in the next class, but as soon as you can get it, it's fine. Because once the assignment starts, okay, you will need to run those tools on. Why don't you start? Okay, there's still 7 days till the next class. That's a lot of time. Let's get started. Let's see what problems you're having, and then we'll see. See, in offline directing, there's a lot of help available if you're in the hostel and all. Just ask your seniors. They all have this. Everybody gets it. By first year, normally most people in their laptops get dual boot. So just ask them. If you are outside the campus, we don't want to tell you do it this way, do it that way, because if you make a mistake or something, then it's hard to debug what you have done wrong. So take some local help, some because this is installing Linux is a very standard thing. Start it, then we'll see. It's not such a big deal. Just look up Google a little bit and just take some help from others, and everybody does it every year. Anything else at this point? Okay, if not, let me hand over. Yes.
So I want to ask that, sir, in these assignments, like how much time will be getting? Is it like
I told you at the beginning, we are discussing it still. Okay. See,
okay, sir.
Some of these things will be at the beginning at least. Okay. Some of these things will be just running the tools and knowing about the tools and so on. Okay. So the question is whether we want you to read during the class, and then because you have to look up the manuals a bit. We'll provide you very specific materials, references to them. As I said, this for many of these tools will not, or for all of the tools actually, will not do all the features. But then if you look at the manual, it becomes very confusing because manual has everything. So we have identified certain references, parts of manuals, then things. So we'll give you, before next class, definitely very clear list of things that will help you in starting off. Okay. And then we'll decide. We're still debating whether to make you read those things and do the thing here itself or do it offline. Let me tell you one thing very clearly. Okay. And because see, this online thing, one side is basically that we miss the interaction and so on. The other side is about this copying and all this business. Now, it's up to you to some extent. You can use the class to learn, or you can use the shortcuts and to make marks in one assignment and all this. So these are tools with lots of features. You don't remember those features or learn them by writing one program, but you will write lots of small programs, do different things with them, fiddle around with it yourself. Because we'll not fiddle around, it's a lab that you will do to learn about the tools. We'll just start you off. So your option. If we give you something to do, online for 3 hours or outside the thing, whether you want to, just take the final thing from somebody, or you want to actually do it and learn it yourself by making mistakes and so on. But these tools will become very important for you later on. That's why we introduced this course, because we thought that early on we want to start it so that you kind of get used to it. But of course, copying, if you get caught, the punishment will be severe. You're no longer kids, but we also understand it's a game between you and us. But my request to you is try to learn, because these are tools that you will learn only if you use them a lot. Otherwise, you will just mug some features. Or you write something from somewhere, and when the real exam comes and so on, then you may be in trouble. These online exams are always, it's an offline exam because most of you are there, then the hybrid we do proctored online or something. We'll decide on that based on, once these guidelines change or something. But even for online, if it's an online exam, you will be under time pressure. You know the standard drill is. And we have our ways of catching at least some of you. But let's not spend too much time on that. That's my request to you. Let's spend time on learning the things rather than trying to do all these stupid things. So regarding assignments, whether you will be in class or outside class or something, we are debating many technical and non-technical issues. We'll update you in the next class. Anything else right now? If not, I have kind of taken quite a bit of time. So let me hand over to Eddie. Eddie, all yours. I'll just stop them.
Okay. So how do I start? Maybe I will just give you an overview of the type of ways of writing codes. I mean, what we actually do in a Linux-based system. That process which we usually teach during PDS physical labs, most of you are, or many of you are not acquainted with that kind of Linux programming environment. So maybe I just start with that. Okay. Then I will just introduce some features of the GNU C compiler, GCC. Okay. So to do that, I need to share my window. Okay. Do you see my window?
Yes, sir.
Okay.
Yes, sir.
Good. So the program development process has, I would say, several components, unfortunately, because this is, oh, okay. Yeah, so, yeah, it's coming. Okay, so what I start with is I open what is called a terminal. Okay, so this is called a terminal. And what is running here is called a shell. Shell is nothing but a command interpreter. Okay. Now we use some kind of editor to write a program. There are many editors. Whatever you like, you can do. You have something like Emacs. You have something like gedit. You have something like Kate. Lots of things. You can directly launch them. For example, here, I can directly launch gedit editor from here. But anyway, you can do it from here also. So I will just write a sample code, something like this. And maybe you do it with this background. Okay, then I write something here. maybe some main function. Okay, so this is just a toy code and you save it with some name. Okay, so it's already given the name test.c. Just save. Okay. So this is how you use an editor. Any editor of your choice. Gedit is, I think, one of the most popular and easy to use editors. And if you, like some other editor, it's also fine. So then the next question is, you have a file called test.c. Okay, it's just created. Then you invoke the compiler. You can run it using GCC or just CC. And it's a good practice to run it with the WAL option. I will tell you what WAL actually means. And then you say test.c. Okay, so it creates something called a.out. Run it. So you give something like 34. And it gives an output like this. Okay, so this is, I would say, the standard way of introducing the programming, I would say, process. And we do it in the first year PDS lab itself, but yeah, last year PDS was completely online. So people have used different, I would say, platforms, even the code block and all this stuff, which does not exactly gives you a feeling about this process. Anyway, so this is editor. Run an editor, edit your code, compile using GCC, and if there are errors, correct those. Eventually you run. Okay, so this is the process. Okay, so I would suggest that you get accustomed to this kind of programming practice. Okay, so that's one thing. And second thing that I would like to say is some brief introduction to the GNU-C compiler. So before doing that, let me highlight that this is going to be our course website. So you will get all references and all this stuff in this web page. So maybe I wait a little bit, you can make a copy of it. Anyway, we will send you an email later. csciitkgpa.ac/in course lab SPL Spring 22. Okay. Okay, so from now onward, maybe half an hour or a little longer, I will give you a brief introduction to GCC, but then let me go to full screen mode. Okay. Incidentally, currently there is as such almost nothing in this page, but we will keep on updating its content as we proceed down the line. Okay. So GCC is a C compiler, you know, and it can compile. Just now we have seen a demonstration how it can compile and generate some executable file which you can run. But there are many intricate features about this compiler that you do not know, and we will introduce today and in the next class something about GCC. First of all, let us see what you do not know. Okay, so what does the GCC compiler do? I mean, what is the process of digesting your test.c and eventually giving something like a.out? Okay, oh, what are the processes involved? Okay, it's actually a complex process. And as Eji was talking about, we use header files. We hash include stdio.h. So what are exactly there in the header files? And why do we need the header files at all? Okay, so these are good programming practices. I will slowly come to these slides. Okay, then what is meant by when you compile something with the -lm flag, you are introducing, I mean, you are using something like square root, pow. Okay, so what is meant by this -l and what is m? Okay, and so far we have seen that some option called wall. So what are the other runtime options or compile time options for GCC? In fact, there are hundreds or maybe thousands of options. We will teach you a few important ones. Okay. Yeah, this is something. How can C programs communicate with this shell? And what is a shell? So you just recall that I opened a terminal. Okay. Now inside the terminal, something that is running is called a shell, which is basically a command interpreter. Whatever you want to do, you tell it, it will do it for you. Okay. Now, C programs can communicate with shells or the shell from which it is running. Okay. We will teach you a little bit or leave it to you for further study. And actually, we will talk about the one-way communication, how you can pass command line arguments to your programs. Okay, so this is one thing. Compilation process involves something called pre-processing. We will see soon. And as AG told, all serious programming projects involve writing multiple files, some .c, some .h. So how can one break one's program into multiple files, or more importantly, instead of how can one write, of course you can write in multiple files, but how to club them together in order to get the final output, which may be an executable file, your a.out. Okay. And what are libraries? Something similar to this math library. What are these called? What are libraries? And in addition to using something like the math library, M library, can you write your own library? We will look at these and some related questions in the rest of this set of slides. Okay. Okay, so I start with the first question. What does GCC compiler do? So what is meant by compilation? Okay. So it's actually a four-stage process. First of all, there is something called pre-processing. Okay. So this essentially involves the processing of all the lines containing this hash directive, like hash include, hash define. Okay. So hash included files are inserted in your code. Second, hash defined macros are literally substituted throughout your code. Okay. So this process is called pre-processing. Okay. And I will give you an example demonstrating these different four stages. The input to this process is the so-called pre-processed C file. Okay. So after this preprocessing, you get some file with all hash includes done, with all macros literally substituted. This file is input to the next stage, which is the compilation stage. Okay. And the output is an assembly language code. It is still a human readable code. We will see examples. And definitely, since this is machine specific code, this is targeted to the architecture of your machine. The next process is called assembling. So after compiling, you still have what is called a human readable code. Okay, it's not a machine readable code. Okay, so the process of assembling converts this human readable assembly language code to something called a machine code or object file. Okay. And this is as such not necessarily ready for execution because there are external things like printf, square root. These things are still undefined in your assembled file. Okay. So a fourth stage partially does that. Okay. So these object files are eventually converted to an executable file in this process. And all the undefined functions, or I would say many of them, will eventually get linked to your executable. Some of these things, external functions will still remain external in your even after linking, once this a.out is generated. So when you run your a.out, some of the functions available in so-called shared or dynamic libraries are loaded during runtime from shared object files. Okay. So these first 4 steps are called compilation, and this is definitely running. At runtime, you have some external loading also. Okay. So pictorially, it's something like this. Your input is a collection of .c and .h files. After preprocessing, you get your headers and macros processed. Typically, C uses this, I would say, this file as .i. This is the extension .i. And the program that is responsible for this is called CPP, C preprocessor. Of course, as far as I know, in modern days, GCC itself plays the role of CPP. Still, you will find this CPP function for, this is the CPP command for doing this pre-processing. And then essentially, this is the basic task of GCC, compiling and generating an assembly code, which usually have .s extension. Then there is something called an assembler. This is AS, the code, the program that does it is called AS. And it generates the so-called machine code. Okay. .o, object files. Okay. These are still not, I would say, executable files. The final process, that is, you include functions from the so-called static libraries, which usually have extension .a. And this linking is a complicated process, and it is done by something called LD. And this eventually generates your a.out. Okay. And during runtime, some functions which are not yet linked to your code will be read from shared libraries, which usually have extensions like .so, shared object. Okay. So one by one, I will demonstrate how this compilation process goes. Okay. First of all, let us write a simple code, something like a demo.c. Okay. So it does something, fairly stupid thing. So first hash include stdio.h, hash include stdlib.h, and defines two macros, 10 and 20. And you have three, this is the main function. You just write it this way: a equal to 10, b equal to a plus 20, c equal to a star b, and then you print c. Okay, so this is just a stupid code. Now let us see how this four-stage compilation eventually digests this file. The first thing is pre-processing. So the preprocessor, which is called CPP, will process all lines starting with hash. Okay, so there is something called a file stdio.h somewhere in your system. What this preprocessor will do, it will completely read that file and insert in your code. Likewise, there is a file called stdlib.h somewhere in the systems include directory. It will simply read that file and substitute it in your code. So this is what hash includes do. Okay. Then the preprocessor will find two macros with names 10 and 20. So whenever it finds this 10 and 20, it replaces this 10 by the definition, this 10. Whenever it finds 20, it will replace this by 20. Okay. And let us see the working of CPP on it. Okay. C preprocessor demo.c. If you do not give a redirection, it will actually print the preprocessed file on your screen. So if I want to store it in a file, I just say redirect that to something called demo.i. I is a common extension for preprocessed files. And now if you look how it goes, okay, this demo.i, essentially don't forget that this entire stdio.h is included in your program. Entire stdlib.h is included in your program. And these are not small files, these are big files. So this is basically a huge file. Okay, maybe it's several hundred or maybe even 1,000 lines long. Okay, so although your code is something like only this much, after this preprocessing, it's a huge file. Okay. And these are all actually Linux commands. Cat means just type it out. Okay. It's an abbreviation of concatenate. Okay. Actually, you can write multiple things. That's why it is concatenation. So it starts with many things, and you will see that hash include stdio.h has this kind of type depths: unsigned char, unsigned short int, unsigned long int, and so on. Okay. So this is what the hash includes do. And then you see that ten is replaced by this decimal 10, and that twenty is replaced by 20. So this is the processing of the macros. This is hash includes. This is the processing of the macros. Okay, so CPP does this thing. The next question is, from the demo.i, I would want to invoke GCC, and I will produce something called demo.s. Okay. So I invoke GCC with the -S flag. It says you just stop after generating the assembly language file. And if I do so and then want to see how it looks like, it goes something like this. You will not understand what these things do. I think in your architecture course, you will start understanding this subtract, move, add, multiply, this kind of things. These are all assembly language instructions. These are registers and other things. Okay. And what is important here is that your main somehow got translated to this machine code like this. Okay. And if you look at something like printf, we have used printf, right? So for the moment, what I want to highlight is that printf is not defined here, but it says something call this, but this is not basically a machine instruction. Okay. This is just written as a placeholder. This is called a stub. And this PLT is an abbreviation of procedure linkage table. Later, when linking is done, during the last stage of compilation, or even during, I would say, runtime loading, okay, somehow this is taken care of. Okay. Anyway, you don't have to understand what exactly this machine language is doing, this code is doing. Printf and exit, what I say, these are left undefined. They will be defined later, and this is just a placeholder. Okay, so that is the second process. Third process is assembly. So convert your human readable machine language file to a machine readable machine language file. Okay, this is done by the assembler AS. Okay, and the symbols. Okay, so you run assembler on this demo.s and generate something called demo.o. Okay, but now this is a binary file. You simply cannot cat it. Of course, you can cat it, but you will see nothing meaningful there. So if you want to see whatever is there inside this in a human readable form, one possibility is you can use this NM, which is basically an abbreviation of name mangling. Okay. So it shows what are the symbols or names defined in that demo.o. How they are implemented, you cannot see. Up to this point, you can see how they are implemented. At least in machine language, you can see. But now you have a binary file, you can no longer see it. Okay, but you see that your main function is defined here, starting from this location, whereas exit, printf, these are still undefined. Okay. So finally, you need to link this demo.o to, so printf and exit are still undefined in the subject file. So this final process is done by LD, but this is a very complicated process. I cannot demonstrate it here. Okay. And this involves linking to many libraries and is a complicated process, but GCC can do it transparently for you. For example, you just say demo.o, it will generate a.out, and then you can run this a.out. You can also see, okay, what symbols are defined in a.out. So if you do this, you have a big list of defined symbols. What is important is that printf and exit are still undefined. But this now says that read the actual implementation of exit and printf from what is called the shared object called glibc_2.2.5. So whenever you run a.out, the so-called executable a.out will tell the runtime system to read the definition of exit and printf from this shared object. Okay, it is not part of your executable. Okay, so we'll see how to build shared objects, static objects, libraries, and all that stuff a little later. Okay, and runtime loading, how do you know from where you are? Of course, this gives you an indication that this has to be read from this. Another comment, Unix comment for this is LDD, and it shows that what shared objects will be read when you run. So it's something like this: Linux VDSO, libc.so.6, and this one, LD Linux x86-64 SO.2. Okay, so if you want these functions, okay, so this is another thing. And if you do not want to build a.out this way, you can anyway run GCC with the minus static option. So in that case, no such shared object will be, I would say, loaded during runtime, but everything will be included in your okay. Everything will be included in your error. I think this is an error. Okay, so not an error. Demo.o or demo.c, whatever. Okay, if you compile with static, then you will get a huge a.out file, because everything that is loaded from these dynamic libraries, from these shared objects, are now included in your a.out. So it's a huge a.out it prepares. And now if you just call this name mangler, you will see, for example, printf is defined. You will also see that exit is defined. And if you run this LDD, it will just say not a dynamic executable. It's a static executable. Okay. So this is basically how you would say compilation proceeds. It's a 4-stage process, but definitely you do not typically involve these 4 stages one by one. You simply call GCC with options demo.c. It will generate the a.out. So it's not only a compiler helping you in the compilation process, it's also a overall manager. Okay, that calls CPP or does the work of CPP, and then AS, LD, everything it does, and eventually gives you an a.out. I have broken it down in several pieces in order to show the different stages. Okay, so this is what this is how compilation goes. If you have a question, first let me hear at this stage.
Sir,
Yeah, tell.
sir, when we hash include, do we write means we just means if that line is replaced by the entire
Exactly.
.h file?
Yes, it is somewhere there. Where it is there, I will tell you. Yeah, it is entirely replaced by that thing.
Yes, sir, and also in the pre-processed file, what is that hash 7 demo.c, that line?
Yeah, it has a meaning which I do not fully remember right now. I read it somewhere. I do not. This line I think you're talking about. Yeah, this one, right? This line.
Yes, yes.
Yeah. It has a meaning. I actually forgot the meaning. Certain names or something. Is there possibly some names or something like that? Okay.
And sir, those triple dots are the means they have not
Oh,
completed.
this is a mathematics triple dot. 1, 2, 3 ... There are lots of things that are omitted here. Okay. Dot. Anywhere I use dot, I mean lots of things are omitted here. At least one or more lines are. At least one line is omitted here. Okay, so this is not what you see in the demo.i file. Okay, so dot is just like 1, 2, 3 ... in a set. Okay.
Yes.
Yeah.
Sir.
Anything else? Here also, you see. After this, there are some maybe 20 lines or something which I just omitted. That's why I used dot. Yeah. Then.
Sir,
Tell.
sir, when I executed LDD a.out in my terminal, sir, it's not a dynamic executable.
Yes, if you compile your code with minus static, then it basically produces a static code. And LDD does not have any information about. But here you didn't compile with static, and it shows the SO files that will be linked during runtime.
Yes, sir. Can you explain the static and dynamic executables?
Look, you didn't write this printf function. You didn't write this exit function. These are functions after all, right?
Yes, sir.
Likewise, if you look at the square root function, sqrt, you didn't write it.
Yes, sir.
By calling or by including math.h, let us take the example of sqrt, square root. So when you include math.h, it essentially replaces that hash include thing by whatever is written in that math.h file. Okay. And that header file, some line of it says what is the input output behavior of sqrt. Okay. So now when you call sqrt, maybe something like sqrt5 or whatever, sqrtn, okay. Now the compiler is happy because it knows what kind of argument and how many arguments this function accepts and what is the output type. When you write this code, until there is a necessity of actually looking at that sqrt code, there is no, it's sufficient, if it is sufficient that you know what is the input output behavior of sqrt. Okay. Now, sqrt is defined somewhere. Okay. It may be defined in what is called either a static library, okay, which I have, we have seen a picture of it. Okay, it's something like .a, or it is defined in a .so file, a shared object file. Maybe both. If it is defined in both, then this SO will be, actually in my machine, this SO will be more, I would say, powerful. It has higher precedence. So now you think of that 4-stage compilation process. If sqrt is defined only in .a file, then in the 4th stage, the definition of sqrt will be read from that shared library, sorry, static library, and it will be inserted in your code. Okay. On the other hand, if sqrt is defined in a shared object like this, then even after a.out is generated, this will not be part of your code. When you run, the definition of sqrt is read from this shared object, and that is executed there.
May I jump in with one?
Yeah. If you have been
So you see why the size becomes so large. Okay. So don't get the impression that only sqrt is taken. So when you have a -lm, mathematical library has implementations of all these functions, sqrt, abs, fabs, all the POW, everything. Okay. So that's one library. Okay. So when you include that as a static library, then this entire piece of code gets added to your code. That is why the size increases basically. It's not that the static code is only taken out from somewhere and just put into your code or something. Okay, it's linked with that basically. So in Linux, actually, for all these mathematics and days, there are 2 versions of the libraries already present, the static one and the dynamic one. And that will become much more clear when Eddie teaches you the static library, shared library, how to bring and show you the sizes and so on. So when you said -static, you said link with the static library. And what happened was it linked everything, and this entire piece of code, not just the sqrt code, got added to your code. So now it is self-contained. It does not depend on anything. That's the advantage. So you can take that piece of that your .a.out and write on any Linux system, compatible Linux system. It is not going to look for anything. Okay, but the size has exploded because you're carrying that entire piece of code along with your code, actually, even though you're calling only the sqrt function. Whereas with the dynamic library, that's why it's called a shared library. Okay, so look at the static library. If you had 2 programs, 1.c and 2.c, both of them called SQRT only, okay, the entire library is added to the code of 1.c and the entire library is added to the code of 2.c. So both their sizes explodes, even though both of them are calling the SQRT function. Okay. Whereas if you use a shared dynamic libraries are shared. Okay. Do not worry about how it is done. Think of it like this, that you loaded the dynamic library. When the SQRT call gets made, the first one, let's say you run 1.c is whatever, a.a1.out or whatever. Okay. Then it runs that code. It sees there is an SQRT call and there is a link to it saying that it is in this dynamic library. So it loads that dynamic library. Then, so now the dynamic library is there. It occupies some space in memory and so on. Okay. And it calls the appropriate function from there. But the entire library, dynamic library gets loaded. Now if you run 2.c also, it tries to load it and it finds that the thing is already there. So it does not load it again. So it's going to call the SQRT from the same place. That is why it's called shared. So static, the advantage is your executable code is completely self-contained. It does not depend on anything while running. You can just run it, but that means it carries everything with you, the complete math library with it. And every single file, output executable file, all the programs will carry the entire library file. All of their sizes will explode. Whereas dynamic says, I just carry a reference to it somewhere saying, as Eddie has shown you with the LDD command, that this function is actually in that shared library at that point. So it looks for that while running. If it finds, it knows where to look for. Okay. So the dynamic library is loaded and only that is called. But the next one, calling it, is dynamic library is already there. So only one copy will stay. The problem is, if you take that executable and try to run it somewhere, okay, and the shared library is not there, then your program will fail. Now you are looking at, right now we are looking at very simple shared libraries. They're in all Linux machines. But then when you build your shared library, okay, and you have an application that is using that library, okay, and you take that application to run somewhere, you have to ensure that the shared library is also there. Okay, so that's kind of the deal. If I, kind of got through to you. So do you have any questions?
Sir, is the dynamic shared library loaded in both 1.c and 2.c?
It's not loaded in any of them. Okay,
So then
it's
how
1.c. 1.c is executable that you compile. It contains a reference to that SQRT function in that math library. Call it, let's talk the math shared library. When the executable run, it comes to that piece, it sees the dependencies basically that to run this, I need that shared library. So the program, don't worry about what, that is actually running your code, okay, actually loads that shared library. There are paths defined to find it and so on. That Eddie will show you later on when we talk about building those libraries. So it loads that. So these are two different components. The shared library is not kind of loaded into the executable of 1.c. It is loaded into memory. Your 1.c's executable calls the corresponding function, and then if 2.c is running, 2.c's corresponding executable, it finds it is already loaded. Okay, so it does not load it again. That's why it's shared. The same one copy of the shared library is there, which both 1.c and 2.c can call. That's the idea. It's a lot of details around it, but that's the basic idea. Does it make sense?
Yes, sir.
Yeah. Whereas with the static libraries, what you are saying is happening. The entire code is loaded with 1.c, and that the entire bundle is the executable for 1.c, which contains 1.c's code plus the entire math library's code. Same for 2.c. Is that clear?
Yes, sir.
Okay, I'm done.
Okay, fine. So yeah, so that's basically the compilation process. If you have any further queries, let us know. maybe we are already 1 hour 45 minutes, but maybe I will just do a little bit to save time from the next day.
I think we can do the multiple files. That is easy.
Yeah, multiple file thing I'll just introduce and we will. Yeah, that's all. So if you have any queries, please let me know or let us know. Otherwise, I will once again switch to the presentation mode. Okay, I think no for the moment.
Sir,
Hey.
I want to ask that some actually editors also produce some .binary files like .bin. So is it like
Possible.
so like what is the use of those .bin files?
No, which editor are you talking about?
So
Be more specific?
like there is something called CP helper. There was a extension, and whenever like it has some input and output, and there you put the expected input and expected output, and whenever I run it, it actually creates a .bin file.
Send me, okay, just send me a one-line mail. Okay. I'll look into it.
It's not clear, but sometimes
What is CP helper does, we have to see what is CP helper is doing. It may not be a compiler.
sometimes what this binary file viewers tell, or you have generated a.out and you want to see what bytes are there. Then you can some editors will allow you to do it. Not editors, I will say. These are mostly readers.
Readers, that's what I'm trying to say.
Yeah.
See, binary files. See, basically when you look at your .c files and all, these are basically text files, because for everything is interpreted as a character and you can see what is there and so on. But then if you think about a file, everything is a sequence of bytes, basically. Whether you interpret the byte as a character or whether it's an arbitrary byte, which everything is not printable character and so on. So binary files, for example, if you have a structure with lots of things, you can write them as, okay, no, that's not may not be a good example. Sorry. Okay. So binary files are like that, as Eddie has said, basically. So anything, including your a.out, you may not make meaning out of it, but it's basically a collection of bytes. So there are many helper functions which are not really compilers. I don't think CP helper is a compiler, okay, which allows you to look at those binary files. And then at the very end, I think we may have a little bit about the format of these files. For example, the a.out file and so on. Okay. And then there are helper things which allows you to, because they also know the format, they interpret that format and shows you certain sections of that and so on, rather than just showing you the raw bytes and so on.
Yes, actually they use the GCC only. There is actually inbuilt in it.
Send me the thing. Okay, let's not stop the class now.
Okay, sir.
I'll respond back to you. Okay,
okay, sir.
Or we will respond back to you. One of us will. Don't worry. Okay.
Okay, so let us switch to that presentation thing. Yeah, so I will give you a brief demonstration of good coding examples, coding practice, I would say. You should break your code across multiple files. Of course, the example is a very small example. Everything can be done in a single file, but this will just demonstrate how I can manage compiling with multiple files, yeah, I mean, over which your entire code is distributed. Okay, so what we will do, okay, first of all, this motivation is already given by AG. So modular programming is a good practice and is needed by or in any large or serious coding project. And I think this motivation is more or less given by AG. So large source files take huge time for recompilation. And if the code is broken down into pieces, then only the pieces that are changed need to be recompiled. Those things that are not affected do not need any recompilation. Okay. And therefore, any large software development is a two-stage process. Generate object files from individual modules, merge the object files into a single executable file, or sometimes merge the object files to libraries, which are also some kind of object files, but they are not called object files. They are libraries anyway. And yeah, user programs can use the functions archived in these libraries during future developments. Okay, so this motivation is already very, I would say, comprehensively given by AG. So I'm just mentioning this thing. Let us look at an example. So what I will do, I will write a multi-file application that can handle stacks and queues. Okay, I can add many other things, but just as a demonstration, I will write a linked list based implementation of stacks and queues. Okay, so we will break down everything into the following files. First, something called definitions.h, which defines a node data type. Because we are using linked list implementations, we will use something like data and a next pointer. Both stacks and queues are will use this kind of nodes. Okay. Then inside a header file stack.h, I will define the stack data type and the function prototypes for stack functionality. Likewise, queue.h, that will define the queue data type, also the prototypes of queue function calls. Then the header file only defines are supposed to define only the new data types, some constants, and function prototypes. But push, pop, enqueue, dequeue, this should be defined somewhere, right? So for that, I will write two files, stack.c, the implementation of the stack functions, and queue.c, the implementation of the queue functions. So neither of these 5 things is equipped with what is called a main function. Okay, so this is a collection of data type and function definitions. And this .c and .c, this is function implementations that use these data types. And finally, I will write a application program which is called stackcheck.c that will contain a main function. Okay, so let us see. Both stacks and queues use nodes. I may define it this way: struct underscore node. This is simple, I mean PDS level C. So you should know this. Type def this as node and a pointer to that node as node pointer, node P. And we only just keep these lines 1, 2, 3, 4, 5, 6, 6, 7 lines in your defs.h. Actually, we include something more that I will come a little later. And then the stack.h will simply rename node pointer as a stack. Okay. And I am going to implement init stack, empty stack, top, push, pop, print stack, and destroy stack. And these are basically the input-output behaviors. And you see that this header file consists of a new type definition. It defines a new data type called stack and the function prototypes. Okay. No further implementations, no implementations. Likewise, in queue.h, I will have a queue data structure containing 2 pointers, the front pointer and the back pointer. Okay. And I have these function prototypes, init queue, empty queue, front, and so on. The actual implementation will be in stack.c. Okay. So alongside this stdio.h, stdlib.h, you also include defs.h. But what I show here in red is that you no longer use these angular brackets when you include defs.h and stack.h. Why? The reason is that this stdio.h and stdlib.h are 2 header files that reside in the systems include directory. And the directory in which you are writing your code will almost certainly be not that system directory. So just say read from the current directory. So you can specify full paths starting from /home, username /spl /codes /something, or relative to the current directory. Okay, so this is you are loading or including header files from non-standard directories. Okay, for that you should use quote, double quotes. We will later see that I can read it using this Angular thing, but then during the compile time, I have to give some options. Okay, and this is followed by all other, I mean, these function definitions one by one. But the main function is not there. So it's not important how you implement your stack. This is just a sample implementation of two of these functions, init stack and destroy stack. Okay. Likewise, when I have q.c, I include def.h, q.h, but within quotes, not within Angular brackets, because they are read from a non-standard location, non-default location. And then you have a definition of complete implementation of these functions. Okay, so you have how many files? Up to this point, there is no main anywhere. Okay, so eventually I will write a function with main. It will include the standard things, and also defs.h, stack.h, q.h, and it will make something like some iteration count is 10, let's say. And it will use stack s. Now this stack s, this is understood because stack.h is included, right? And stack.h in turn uses a node and node pointer data type. Therefore, you have included defs.h, so no problem. Likewise, this q data structure is defined in q.h, which in turn depends on node and node p, defined in defs.h. And you also know what init stack, init q, these functions behave. For example, this outputs or returns an initialized stack. This returns an initialized queue, and stack.h has this prototype definition. Q.h has this prototype definition. This one, this one, this one. Okay. So when you compile, the compiler will be happy. Okay. But everything now is in your directory. Okay. So this is the only thing that contains main. But the point is that you have not included stack.c. You have not included q.c. So the actual implementations of push, print stack, enqueue, destroy queue, init stack, these things are not there. What hash includes does, it simply replaces this line by whatever is written in your defs.h. Similarly, it simply replaces this line by whatever is written in your stack.h and so on. Okay. And the preprocessor also replaces iter_cnt by 10. Here. Okay. Still, there is no definition of init stack, init queue. Okay. Actual implementations. Okay. They reside somewhere else. Okay. So eventually, I have to club all these things together. Of course, I could have included stack.c and q.c here. That would also serve my purpose. But anyway, we will not do it in order to show you this thing. Okay. Okay. So what you can do, you can say this is C minus W all the three files together. Stack q check.c, stack.c, q.c. It will generate some error out. Okay. Which you can now run. Okay. This is fine. Not a big issue, but the point is that if you write another code, okay, that uses the same stack and queue functions. It's preferable that you generate individual object files from this and this. And we will not talk about how to implement libraries in this class. Okay, but anyway, let's see. Yeah, this is an option which now I mentioned generates most of the relevant warning messages, not all. Okay, most relevant warning messages. What it includes, we will see later in a later slide. And this is an important thing. Another option is -o. So GCC -w all, you can say -o some executable file name. If you do not specify this, then by default, GCC generates an a.out file. But now if I want to generate some other name of this executable, I can just say -o that executable name. Okay. And it's important to note that never forget the actual executable file name. This is a common mistake done by many of you. In PDS labs we have seen. So you just forgot, just -o, you just forgot it. Then what the compiler will do, it will replace the stack queue check.c by your object file, I mean by your executable file, and you have lost the stack queue check.c. So be very, very careful, right? Don't do this. So never forget an executable name after -o, otherwise your C files may be overwritten. Okay, and there is no way you can recover stack queue check.c, the original stack queue check.c. Okay. Anyway, so you can, yeah, tell.
The stack.c is the executable file, right? What is my app here? What is my app here, sir?
So this is just a name. You can run by /myapp. Instead of a.out, it will generate myapp.
No, I want to correct. Stack queue check.c is not your executable file. It is the file that contains the source code. By doing GCC, you are creating the executable file. If you do not do -o, by default, the executable file will be called a.out. So you want to give some other name to your executable file, you give the -o, the name of the executable file. Stack queue.c is not the executable file. It is just the file that contains your main function. In C, you know exactly one file should contain the main function. So that's it. Is that clear?
So how will this myapp work here, sir?
No,
You just run it ./myapp. Just like you have done ./a.out, it's just a name.
Yeah, instead of a.out, it will generate an executable file called myapp. It's just a name.
If you don't tell the system anything, it does not know what to name it, so it names it a.out always. But now think you did this and then you have some other program and you run that, compile that, then this a.out will be get wiped off. Then you have to compile MyStack, this is the same thing again. So it's just a name. If you don't know anything, or the system does not know anything, it does not know what to name it, names it a.out. If you want to give it some other name, tell the system what name you want. That's what you're doing with the -o, myapp. Myapp is just a name.
Yeah, you can also say myapp.out.
Anything.
Any name you give.
Is that clear?
Sir, will there be any folder with myapp, or it is just a name?
Not folder, it's just a name of a executable file.
Instead of a.out, whatever you supply, that will be generated.
See, if you do ls-l, you see this is a.out coming in.
Instead, it will see
myapp. It's just another file.
Yes, sir.
Okay.
Sir, does the order matters here in the first line?
It may matter, but I think it will not matter in this case. It will not matter because individually it can contain, I mean, this can compile any of this because you have included relevant headers. Stack.c requires dev.h, stack.h, so it is there. It is there. So independently it can compile everything. But it requires a function with main file. So Here the order is not important. This is happy if it finds main function anywhere in any of these three things. This order will not matter.
But when you do libraries, you will see that minus L, the order matters.
Then there the order matters.
Yeah, here it does not matter. Only thing you have to ensure that there is, when you compile these many files, there should be exactly one file with the main function. Otherwise, the compiler is confused where is the starting point.
Yeah, for that matter, not only main function. Any function must be defined at most once.
Yeah.
You do not have push defined here and here. And
yes,
here.
yes.
Of course, main is the main entrance to your executable. Okay. Okay. So this is if I want to generate a single object, single executable file. What I will now demonstrate, I can actually generate an object file from stack.c, an object file from q.c. Eventually, I will club together this with those object files. Okay, so let us see how it can be done. So now I have to compile using the -c option. Okay, this option does not generate an executable file. Instead, it generates what is called an object file. It's in machine code, but it's not directly executable. And it does not require a main function. Okay. Some file with the extension .o is generated. And this does not generate an executable file. And even if main is there, it will not generate an executable file. Okay. So now let us see gcc -w all -c stack.c. gcc -w all -c q.c. You see that after this, if I make ls -l, then you see that the stack.o is generated, which is the result of this first line of compilation. The stack.o is generated. The result of the second line of compilation is this q.o. And as your question, somebody raised the question, then you make the final compilation of this .c file, stack.o and q.o. Okay, and you want to give the name myapp. Then if you see ls -l, you will see instead of a.out, this file is generated, myapp. Okay, so that was the question, right?
Yes.
Then instead of running a.out, you can simply say /myapp. Something will happen. Whatever is written in the stack ifsec.c, it will run. Okay. So now you understand what is called this -c option.
Sir?
Yeah, tell.
Sir, in the third line of the command, sir, what is the input file that we are giving?
This one, and this one. This function, this C source file with main and two precompiled object files, stack.o and q.o.
Okay, sir.
Okay. So we are actually going or inching closer and closer to libraries. So we will actually build a library out of these object files. Anyway, we will see. Not today.
Sir?
These are like libraries, but still not of the same form of a static or dynamic archive. Yeah, tell.
Sir, when we write the code in code blocks, we get .o files, but not with Visual Studio Code. Is there any reason?
No. See, those questions you kind of ask us offline. Okay. It all depend on what options. See, because when you write the code in code block and you're compiling, see, if I don't give this -c option, okay, then GCC will also not give us .o. So that's why we want to teach you this and not the GUI wrappers. Okay, like code block or something, one specific ID. Okay, so because see, for example, if you look at code block, okay, you will have some default setting for GCC set there. First of all, you have to select GCC. There's a main GW which is equivalent to GCC. Okay, and then there's a default setting. Now, if the default setting says that you generate the C, you compile like this. Now you see, if you look at this listing, you can get both the .o files and the .c files. Okay, but if I did not do this, if I just directly said GCC, Abhijit, can you just go back one slide?
This one, right?
Yes. You see, when I compiled everything together, I did not get the .o files. So it just depends on what options I use basically and what steps did I follow, which are in the default. That setting may be different in CodeBlock versus Visual Studio, which is precisely one of the reasons why we don't want to stick to one particular IDE, because then you have to show that you will learn how to set the IDs, defaults, and so on, but you don't learn basically about the process itself. Am I clear?
Yes, sir.
Okay. So don't worry about that.
Excuse me, sir.
Yeah, tell.
So functionally, is there any difference between the previous method and this method where we are first creating the object files and then running the code?
Actually, you see, there is no difference. What is the size of this my app? 17640. And if I do it the other way, what is the size of a.out? It is also 17640. These two files should be identical. Okay. But we are teaching this -c option because we do not often want to link this stack.o and q.o to always to this. There may be some other things. In fact, that's the reason. We will eventually, what we will eventually do, we will generate something like a static library, a dynamic library out of these object files. And if we put those object files, put those libraries somewhere in your system, then using that -l, whatever that name of the library, like -lm, okay, you can link it. Okay. In fact, you see, you did not write square root.h, right? You did not write POW. You did not write FABS. Okay. Somebody else wrote it. They generated object files. They eventually clubbed together all these object files, one or more, whatever they wanted to write. It's up to them, into the math library. Okay. So the basic or the first ingredient of this compilation process is generate individual object files. And this example precisely does so. As such, there is no reason of doing it for this simple example. But when you look at library generation, building libraries, we will see why this -c option is very, very useful. Okay. Now, for this toy example, there is no point doing this. Okay. This is just a demonstration of how you can generate individual object files from C source codes. Okay.
All right, sir.
Okay.
So this, can I add a couple of things?
Yeah, you do.
So see, the other thing you see, as Eddie said, for this simple toy example, there is absolutely no functional difference, which could have done anyway, doesn't matter. Okay. But again, always think about, I would like you to think about that real world thing. See, think tomorrow you write another thing which uses only a stack, but not a queue. Okay. So the stack.o is already built. The work to come, so what would you have done if you have not generated the .o already? You would have done GCC whatever -wal, that file, say stack check dot something, call it something else, .c, stack.c. So then see that object file is getting generated in the backend again anyway. Whether you generate it separately and you keep it, or GCC deletes it at the end. Okay. So implicitly or explicitly. So this is kind of when you generate the stack.o, and that Eddie has said correctly, that it has something to do with libraries later on. You have kind of kept one part already done, okay, so that if somebody needs to do stack.o again, use stack.c again, they don't have to start from stack.c. Part of the work is already done. They can just link with stack.c. Okay. And again, I would request you to kind of slowly get into this mindset to think about large projects. In this case, it does not matter. Once file, basically, whether you have created stack.o, small time you have saved or not, hardly matters. But when you have lots of them, okay, and you want to link with maybe 100 files, then whether those 100 files you will redo from scratch or the .o files are already made for you, either compiled into a library or separately if you want to know only subset of them, okay, matters a lot in terms of compiled. Okay. Is that clear?
Yes, sir. Yes, sir.
The other thing is there is no functional difference, but there is a convenience difference. You see, if you do it this way, you get all of those .o files staying there. Now again, it's only a couple of files, so it doesn't matter in this simple example. But again, if you think about that, you have been doing it for a long time with lots of files, there's a lot of .o files that get generated. And then they may not necessarily be small files like this. And then you have to manually clean those .o files. If you don't need them, don't have them. So idea is you create .o files if you are going to build libraries out of them. And when do you build libraries out of them? When whatever you have put in that .c file that you are going to create the .o file of, there are things that you expect to be shared by many different functions later. If it is not to be shared, there is no point keeping the .o. You compile it once, forget about it. But then the other side will come. There is another aspect of it why in the other case also you want to keep it. When AD teaches you make, you will see that what if you only change stack.c and so on. Okay, anyway, no, that doesn't matter. Sorry. But mostly if you want to share, you do stack.o, q.o, you generate them. If you don't want to share them, in this simple example, it doesn't matter which way you do it. It's kind of hard, as I said, why I spent a little bit of time at the beginning that you have been so used to working with small programs, 1 file, 2 files, and so on. It's tough to think about the requirement when you do a large thing. Okay, so kind of try to think from that angle also. As you go on, it won't happen in a day, but as you go on. KD, I'm done. Sorry.
Okay. Okay, so maybe I just stop with this. It's already a long class. So yeah. So we have hash included stdio.h, whereas we have used this double quotes for deps.h. So why? Because if we use this angular brackets notation, it is expected that whatever is to be included lives in a default directory where C header files can be found. And these default directories are usually system dependent, but you usually always have hash include, hash user slash include, not hash, slash include, slash user slash include. Yeah, more or less things, user include, user local include. In some machines, you also have just / include. Anyway, so the C preprocessor knows where to search for this. Okay, but what is not included in this standard list of directories is your current directory. Okay, dot is not there. Okay, so header files residing in non-default directories should be included using the double quotes directive. Okay. Here you can mention something. If you do not specify any, I would say, explicit directory name, it implies current directory. Otherwise, you can specify starting from this slash, okay, or relative to dot. Okay, so you can do that, but there is an option, compile time option, okay, where you can include dot in this default list. So if you compile with the -i option, this is followed by dot. With or without a space, it doesn't matter. You may add a space here. You may not add a space here, whatever, it's your liking. Okay. This says that now treat dot also as a, I would say, directory, standard directory, where the C processor will search for header files included with this angular bracket directive. If so, if I do that, then I can write this way. Okay, because now dot is a part of the standard search path for header files. So the preprocessor will search dot in addition to these things. Okay, but this list is usually system dependent. Okay, these are typically the commonest ones. Usually it's there in any Unix system, in any Linux system. Okay, but if you compile it with this, then you can actually use this angular bracket notations. Okay, and it will not.
Is this change permanent?
No, no, no. It is just for this compilation thing. Okay, it's not permanent. If you, for example, compile the next one with this, without this, then this will not work. But anyway, but since you have raised this issue, if we want to make it permanent, how can we do it? Okay. Yes, so this is what the next slide says, and I think I should stop after this slide. Yeah, so that requires you to understand what is called shell variable.
Vijay,
Yeah.
I think let us stop at that, because now you will get into environment and shell and so on. Little bit you have to.
Yes.
Yes. Maybe we can just stop at -i today. This is my suggestion.
Okay, maybe I will just mention what to do. You will understand this.
Yeah, blindly mention maybe rather.
Blindly mention this. Yeah.
Environment.
So multiple directories can be added as a colon separated list. Directory 1, directory 2, directory 3. And now there are lots of issues. Dot can be one of these directories, and you can say dot, 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 or /home, many things. And now there is some shell specific comment. If you use, for example, Bourne shell, you can do something like this, dot, this and this, they are included in the default search directory. And if you use some other shell, of course, this comment is usually shell dependent. For the moment, you don't have to understand what this export does, what this environment setting does. Okay. Now the point is that if you do this, then actually you do not require this -i flags, -i options. Okay. Because whatever is called the C_include_ path, it also now contains these other directories. Okay, you do not need it. But then if you reopen the shell, okay, then these definitions are lost. You have to do it again. And there is a way to permanently do it. You have to write in some profile file or RC file. Let us come back to that thing later. This is for the moment, just you learn how to do it. And this is just mechanical way of learning. Yeah. So I think this is already good enough for first day. So next day I will start with libraries, static and dynamic libraries. Yeah, so yeah, I think I should stop here. It's already.
Sir?
Yeah, tell.
Sir, can you show me the code of defs.h?
No, little later. It's still demo. Let me see. It is just this. Yeah. It just defines
Sir, here?
this.
Sir, both stacks and queues use this defs.h directory, right? Header
Exactly.
file.
Exactly. Because both use
So,
nodes.
sir, why we need to explicitly mention, I mean, include this defs.h file in our main file?
No, I don't understand your query. So otherwise, I have to write these definitions twice, and in q.h and stack.h.
Sir, he's asking that.
Yeah. What is
Sir
the
is
question?
asking that if in the stack.h and q.h the defs.h is already mentioned, so why do we need to write it in main.h, main.c also?
Okay. Let's see. Let's look at this stack check.c. Okay. Yes. That's what I mentioned. Okay. Why do I need to hash include defs.h here? That's the question, right?
Yes, sir.
I think so. Yeah.
Okay. Let us see what is defined in stack.h. Let us look at that stack.h file. This is stack.h file. Node P is not defined there, right? Stack is defined, but it's defined in terms of node P.
Yes, sir.
Okay. So stack is defined, but that definition requires node P. For that, you have to include defs.h.
So this kind of it's a good question. This kind of brings out the other problems. You see, when you have when you include so many header files and the header files include 2 levels down header files, how do you know which header files include what and what should you include, what should you not include? I'm just pointing out problems. These are all problems that we've actually gone through. Okay.
In fact, I will tell you a easy way out. You just include one header files, which will in turn include all other things. And we will install this in some system directory so that.
No, it's in the real software. It's not going to be that easy because that will load the code of many files which may not need many parts of that header file.
That's true.
Yeah.
If you want to select,
so you don't have. So you again put certain type defs are used by almost everybody.
Yes.
So you put them in types file and so on, which everybody uses. So you again break up basically.
Yeah.
But then that so class is almost over. This brings in what should you put in the header files? Because hash include will include anything, right? You'll just copy it. So as Eddie pointed out, you could not, somebody asked and he said, then you could have include hash include stack.c hash include q.c also. And then you could have just compiled stack q.check.c. You don't need to mention stack.c and q.c, right? So here is, I'll ask you to explore more, but here's the golden rule. The header files should contain only macros, type defs, preprocessing directives like hash include. There are many other preprocessing directives, prototypes. It should not contain any code or any variable declaration like global variable declarations, anything that takes storage. Header files will only contain preprocessor directives, type defs, and function prototypes. No code, no global variable declaration. And again, even though you can include stack.c, q.c, it is never a good practice. So you will never see code which actually includes .c files. Hash include are always with respect to .h and others. There are some other types of files sometimes, but you never include .c files. If you have another .c file that this file depends on, you do this multiple file compilation and so on. So this week, kind of install Linux, play around with basic commands if you're not installed, the basic file system, how to go around directories with .cd. Some of them open a terminal window. Just play around with it and then play around with GCC. We'll upload the slides and everything. Okay. No assignments, nothing. And then next week we'll finish up with this and actually start doing some assignments.
So does order of header files also matter?
What do you think? Here, if you have done hash include stack.h, what do you think would happen? First, before defs.h, you do stack.h.
But there could be no two header files, like they are dependent on both. Both.
Exactly. So you see, if you hash include stack.h, stack.h uses that type def node p. That node p thing it uses, but that is type def in defs.h. So when you try to compile, you will get an error because it hits node p, and at that time, compilation is from the top. It hits node p, but the type def is not there. It does not know anything called node p. So yes, the order is important.
Yeah. But however, you can simply swap this stack h.
Yeah, stack and queue we can swap.
They are independent.
But they are not dependent on each other.
So here for running the stack check file, we are including stack.c and q.c, right?
We are not including stack.c and q.c. I want you to get your terminology. We are compiling stack.check.c with the file stack.c and q.c. We are not including it. The code of stack.c is never copied into stack.check.c. Do you see hash include anything .c here? Nothing, right?
So, sir, for using the functions in the stdio.h or stdlib.h,
there is only function prototype in stdio.h. Okay, the function bodies are in the standard C standard library. Yeah, go ahead. Now finish your question.
Yes, sir. Now it is fine.
Yeah, it is in the glib, whatever you have seen, right? glib 5 point something something SO.
That's the dynamic library for the standard.
That's the dynamic library. It's there.
Sir.
Yes, go ahead.
For those Angular bracket libraries, so here also we are including just the .h files. So why do we not need to compile multiple .c for these files as well?
There is no .c file. Hash include is just copying the files. It is first putting whatever is in stdio.h there, just copy. Then whatever in stdlib.h, just copying. Then defs.h and stack.q.h. Now you have got something, the complete code. And it's compiling that.
So that I understand. I'm asking that in the Angular brackets .h files also there are just prototypes and macros, right?
Yes.
So for those there would be some corresponding .c files as well.
This is in the standard library. Those are in the standard library.
So why do we not need to include them while compiling?
Okay, because GCC automatically looks for it for the standard library.
Okay.
This is done during linking.
Linking, it automatically includes the standard library.
Okay.
Any other questions?
Sir?
Yes.
Sir, suppose I need to write my .h file. Suppose I wanted to write my print.h file. Sir, in that header file, I want to create a new function which only prints hello world.
You never create a function in a .h file. What you will do is, you will put the prototype of the function in the .h file. Okay.
So only prototype.
Only the prototype.
Yeah. Once again, let us look at this.
Yeah.
This is a typical thing.
You see, there is no code in there. There's type def and there are prototypes.
And there may be some hash defines there.
Hash define macros, any preprocessor directives can be there. And you will write a separate function called print.c or file called print.c or something. Put the implementation of that there. In that function, you will include hash include print.h, so the prototype comes on top. That's the practice.
Sir?
Yeah.
Here in this particular file, the defs.h is not included here.
Right.
Yes,
Because it is not using anything for defs.h. Do you see anything that is there in defs being used there? Oh, node P is used there.
Yes, sir.
Yes.
Sir,
Yeah. So yeah, go ahead. Go ahead.
sir, should it generate an error because node P is not
No,
defined?
because
you
when
are
we
not
call
compiled
stack
Q.H, right?
you have not compiled yet, no? See, we just go to stackqcheck.c.
Yeah. You are not compiling this individually.
Right.
What you do, maybe this one. It will first include this, and then node P is understood. Then it will include stack.h. Then stack is understood. Then Q is understood, and then this part is fine.
Okay, sir. Yes,
Okay,
sir.
which is why we said that you cannot put stack.h before defs.h, because then it will complain.
Okay, sir.
That will complain only during compilation. When you are creating the file, you are just typing text into it. You can type anything. And when you compile, then all these rules are checked.
Sir,
Yes.
so can't we add that include defs.h in the stack.h file instead?
Yeah, sure.
So then we wouldn't have to look for the order instead.
Right. But then your defs.h gets, if you put it in stack.h and q.h, okay, it gets added twice. Why don't you try these things out? These are the things that it's a very good question. Okay. Just try this thing out, see what the result is, and try it. Either you will get an error or you will not get an error. Right?
Yes.
See, you will see this hash include str.h everywhere. So just write two C programs, okay, with hash include str.h, one calling a function in the other, which is what this is doing. Run this. You put up the slides, run this and see what happens and try to explain. Yeah, and we'll see. It has made beautiful slides and you will have lots of material on the slides, but at the end of the day, you have to run the tool to learn tools and you have to run it with multiple files. Don't just do one file and then you will know, but then you will forget this. And you have to kind of practice this as you go on with your programs. Just run it, okay? If you are confused, let us know. Anything else? Okay, then it's a long class. Eddie, I think we should fold up, right?
Yes, I think this is, yeah.
So what we will do is we'll put up the slides and some materials for GCC on the net. Do we put up the slides today, Abhijit? Or
this is not fully done.
Done, so when we may not put it up. You just look for GCC. Why don't you fiddle around? There is no assignment, nothing.
Of course, the first initial pages we can do.
Yeah, maybe up to this we can put up. Because we don't want to go too much ahead of the class, because there is, just learning the different features is not good. You need to go in depth into them to see what is happening and so on. So fine, we'll put up to this much. We'll put up some material. Or materials are for first week, you can just search in GCC, for everything is there. And get familiar with Linux if you're not used to. Another thing we'll do is we have some TS for the lab. So sometimes within the next couple of days, we'll allocate TAs to groups of students and we'll let you know their contact emails and let them know yours and so on. So you can also contact them when you get stuck. But again, my request to you is practice yourself before you ask questions. Because otherwise we'll just get answer to that one question. But you practice, you get into it, try to explain things, you'll learn a lot better. So anyway, let's get started. We told this an experimental lab this time, just starting for the first time. So we'll see how it goes. Any other thing?
Sir?
Yes.
Sir, where can I find the recording for today's class? Because
It will
there's
be in
not...
Teams in the standard place.
Sir,
no. We have to add them to the. Otherwise, they cannot.
Oh, because this guest now through the links.
Yeah, they cannot access in the chat.
So okay, I think we'll send you a team code to join.
We'll send you a team code. Yeah.
Okay. Actually, we thought that because many of you are supposed to start in hybrid, we thought we'll only admit people who are not in the campus. But now God knows how long it will go in online. So fine, we'll send you the team code to join the course, and then you can get the record. Any other thing? Okay, if not, thank you.
Thank you, sir.
Okay, bye.
Bye.
Sir, do you recommend